Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And first of all, it's my pleasure to introduce my colleague Tony Hoare. Tony is a consultant principal researcher at Microsoft Research, now working part-time for us. And when I saw the summer school webpage just earlier this morning, I thought, oh, he's been quite humble in his biography because there's a lot of detail missing. So I will fill in some of that detail, but not all of it. Because Tony had a long career in computer science. He studied classics and philosophy in Oxford. Afterwards, he had an academic career at various universities, at Queen's University in Belfast. He was in Oxford and also at Moscow State University in Russia. He's been now a researcher with us for quite a number of years here in the Cambridge lab. Tony is well known for Quicksort, the Hoare Logic, and CSP. And he won the ACM Turing Award in 1980 and a number of awards afterwards. Too many to go into detail. Welcome, Tony, and we look forward to your talk.
Well, thank you very much, Scarlett, for that pleasingly short but very flattering introduction. And thank you all for your welcome and your attention. I consider it my privilege and certainly as a pleasure to address an audience of this summer school. You are all researchers, or most of you researchers from universities around the world, just at the beginning of your research career. I have exploited this opportunity to tell you about a topic in computer science which has interested me throughout my research career, which is at the present time a little bit longer than yours. And I hope it will, and it continues to do so. And at the same time, I will tell you something about myself, something about my motivations, the ideas which helped me in my research, and maybe some which did not. I expect my talk to last about 50 minutes. I'll spend about half of it talking about the laws of sequential programming, and the second half on concurrent programming. I hope to leave 10 minutes at the end for questions, but you're welcome to ask questions before that if you wish. And I'll start by asking you some questions about yourselves. First question. Before this school, how many of you had heard of the laws of programming? Oh, excellent. Well, I hope at the end of 50 minutes you will know quite a lot about them. In fact, more than most programmers do. So there's no really point in asking the remaining questions, except that I hope that in my talk I will be able to answer them myself, and so at the end of the talk you will be a little marginally wiser. My own answer to the questions could be summarized very briefly. The laws of programming are a collection of mathematical equations, roughly the level of the algebra that you learnt at school, simple algebraic equations involving familiar algebraic properties. The laws are widely used, although maybe not everybody knows it, in the development of software that you use every day. Operating systems, compilers, program checkers, program analyzers, and also, to a lesser extent, in the software for the cars and the trains and the aeroplanes on which you travel. Finally, the laws have been proved true of a simple programming language, is what I will describe in my lecture, which was invented by one of the great logicians and mathematicians of the last century, Stephen Kleene. In 1956, he published a paper entitled A Representation of Events in Nerve Nets and Finite Automata. One of his aims was to represent events occurring in the nervous system of organisms. He therefore made his contribution not just to the theory of programming, which is what I will be interested in, but the foundations of computational biology, which I know is of great interest to many of you and has been treated well in previous lectures of this summer school. Great. So I will talk about Kleene's regular expressions. It's a sort of a programming language which is used to program finite state automata or to specify the behavior of such machines. Execution of a program was represented as a string of events or actions which occur sequentially while the program is being executed. Regular expressions are widely used today to specify protocols for dynamic interactions of components of a distributed or concurrent computer system. These are the notations which I shall use for regular expressions. The semicolon denotes sequential composition of strings of actions. Execution of the first operand P is followed by execution of the second operand Q. The union operator denotes a choice between its operands. Only one of them is actually executed and the other one is ignored. The numeral 1 denotes the program that does nothing. Here is a sample of the laws of regular algebra which apply to regular expressions. They all appeal strongly to your programming intuition, which you have developed over several years of practical experience of programming. The associative law at the top of this slide says that if a program asks for three actions in a sequence, it does not matter in which way the actions are bracketed 2 by 2. The next law states the obvious fact that if you do nothing before doing P, this is the same as doing P. The laws for choice are the same as those for disjunction in Boolean algebra. A choice is associative, it is commutative, and it is idempotent. A choice between P and P itself is no choice at all. You have to choose P. The final law is a distribution law which describes the interaction between the sequential operator and the choice operator. The left-hand side describes the execution of P followed by just one of either Q or R. The right-hand side describes a choice between the execution of P then Q or P then R. And the distribution law merely says the same thing as it does in ordinary algebra, that the choice can be made before the sequential composition, as it were at compile time, or it can be made while or even after the execution of P at runtime. But choice must be made. Now, going slightly more sophisticated, I'm going to introduce what is known as the refinement ordering in programming. Has anybody of you heard of the refinement ordering of programs? Oh, lovely. So here it is. P, I will call it below. P below Q means just that every execution of P is also an execution of Q. In other words, the executions of P are just contained in the executions of Q. As a result of this, P has less executions, it's more determinate. It's easier to predict what it's going to do. whereas and furthermore, it's easier to control. What it's actually going to do is going to be more tightly controlled by P than by Q. Conversely, Q is more abstract. It describes more phenomena than P, and therefore it's like an abstract theory in which a lot of the detail is ignored and the essential abstraction is made clearer. Abstraction, of course, is a property of specifications, and all my P, Qs, and Rs are going to apply to regular expressions, whether they are used as programs or as specifications. And the refinement ordering applies to them all equally. For example, if P is a program and R and S are specifications, P below R means P satisfies R as a specification. Everything it does is allowed by the specification P. And R below S means that R implies S. If R is a design, a slightly more concrete specification of the eventual product, of the eventual program, then R below, and S is a more abstract specification, then R below S means that R is a more concrete description of every product that is described by S. It is slightly unusual to use relations between things that are as different as programs and specifications. In fact, they're often expressed in different notations. We can use more powerful notations in our specifications than we do in actually writing programs. But the justification is that in the algebra of them is the same, and all the proofs of the refinement relation are the same, no matter whether the operands are of the same kind or whether they're of different kinds and going to be used for different purposes. For example, specification and design rather than just execution. Refinement can be defined algebraically in terms of the choice operator as saying P below Q just means the union of Q and P is equal to Q. Since P is contained in Q, its union with Q leaves Q unchanged because all the executions in P are already in Q. Now, the law that I have given you the definition enables me to prove some theorems on the basis of the axiom of distribution. And the two theorems I show at the top of this slide are immediate consequences of the distribution of semicolon through union. But I can also express the covariance property by a proof rule rather than by equations, or in this case, inequations. Can I use the word equations to stand for inequations as well, please? Because, of course, there's no real distinction. Every equation is just two inequations. Every inequation is just half an equation. The proof rule says, if you know that P is stronger than Q, then you also know that P followed by R will be stronger than Q followed by R. And similarly, R followed by P will be stronger than R followed by Q. This rule is a special case of a very general principle in which engineers have an intuitive belief. If we take an assembly, an engineering assembly, say a board of a computing device, and we replace one of its components by a stronger one, a component that has tighter tolerances and will accept more variation in the environment, is more deterministic in this sense, and produces a more reliable result, If you change the component, improve it in this way, then you can only improve the whole assembly. And this is basic. Whenever you replace a bulb or any component of a system by one that is better, the resulting result will be better than the original. Now, the proof rule notation. The proof rule tells you how to extend a partial proof by adding more lines, by adding more statements at the end of the proof. So a proof rule comes with a line in the middle. The antecedents are written above the line, and it says that if you have proved the antecedents, then you may also write any of the consequence written below the line as the next line in your proof. So proof rules help you to write proofs, but they are all based on algebraic laws, and they can all be proved from algebraic laws, like this one can, using the definition of the refinement relation. Here are some more proof rules for before. The first of the rules on this slide are a formal statement as a proof rule of a very important property of refinement, that it is an ordering, it is transitive. And the second states that it is antisymmetric, that if if P and Q are below each other, then they are equal. Now, let's move on to applying some of this knowledge to the proofs of programs. I will begin my talk with an account of how the laws can be used to explore and prove properties of the programs that you write. I'll also describe how they give guidance to an implementer of a programming language which obeys the laws. Right at the beginning of my career, my academic career, I wrote an article entitled An Axiomatic Basis for Computer Programming, which essentially describes my interest in this subject. In 1968, I moved from a job as a programmer and researcher in the computer industry in Britain to a chair of computing science at the Queen's University, Belfast. My motive for making this move was that I wanted to conduct long-term research into the theory of programming. And I realized that my chosen topic of research, the theory of programming, would not be likely to be put into practical use by industry for at least 30 years ahead, because 30 years was the date in which I was due to retire as an academic at the standard retirement age. I wasn't worried by this. In fact, it was exactly a point that attracted me to this subject of research, because it meant it would last me all my life as an academic. Because once the results of research have been taken over by industry and incorporated in industrial products, the results are no longer original. And you can't conduct academic research into topics in which the results are already part of consumer products. The other reason is that any further development of the theory would be conducted in industry itself using far greater resources than are available to an academic researcher. So I was protected from this problem by the fact that nobody would use the results of my research until after I'd retired, so I wouldn't have to change over in the middle of my life. And nor I did. I actually retired from academic research in 1999, and very fortunately took up an offer of a post at Microsoft Research in Cambridge here. I found that my prediction that the results of my research would not be used in industry was entirely correct. In the early years of this century, the when I was working for Microsoft, the scene changed dramatically. At that time, Microsoft Windows was suffering from a series of malware attacks, several of which disrupted the entire commercial and economic life of the world for several days. They were estimated, each of them, to have cost the world economy the sum of around $4 billion, which Microsoft thought was rather a bad idea. So Microsoft developed a program analysis tool exploiting the results of academic research, most of which, of course, had been done after I'd started this line of development. And the tool was able to detect the vulnerabilities that posed the most risk of repetition of the malware attacks. And and indeed they were installed and they were used on all of Windows code, and they had the required beneficial effect. And similar tools are now provided as program analyzers in modern integrated development environments like Visual Studio or Exchange. The basic concept of my axiomatic basis of computer programming was expressed not algebraically, as I would now express it, but rather as in a new notation called a Hoare triple. The purpose was to help in the proof that all possible executions of a program Q, when started with a given precursor P, will exhibit some desirable property R. So PQR are the three operands of the triple, and it's written with curly braces as shown in my definition. The definition, the algebraic refinement equation on the right-hand side of that is a definition which I discovered only quite recently, enables me to translate algebraic notations into the notations of the Hoare triple. The interpretation of the notation is if P is, which is called the precondition, describes what has happened so far, and Q is now started and executed to completion, then the trace of overall execution, when both P and Q have been executed, will be satisfy any specification R. Now the rules for the proof of the correctness of programs were mostly expressed as proof rules of the form that I show on this slide. This slide covers the proof rule for sequential composition. It says that if you have proved that P followed by Q satisfies the specification S, and S followed by Q dashed satisfies the specification R, then you can deduce that the sequential composition, Q followed by Q dashed, will satisfy the specification which has P as its precondition and R as its postcondition. Now that rule can be proved quite quickly from the law of associativity. But I cannot prove the associative law from the sequential composition law. Now, a calculus of communicating systems was the subject of research of my friend and colleague Robin Milner, and he published his work first in Springer Notes in Computer Science in 1980. The question that Milner wanted to answer was one concerning the correctness of an implementation of a programming language. This question is formalized by giving a set of triples, which are known as transitions, which collectively form an operational semantics for the language. He gave a canonical example of the rules in the definition of an abstract implementation of his concurrent programming language, or process algebra, which came to be known as CCS, a calculus of communicating systems. Now, the Milner Transitions he introduced to show how an implementation can generate a single execution of a program R, because an implementation only needs to find one of those many possible executions of R, depending, of course, on its input parameters. It doesn't have to consider all executions, which is what I considered in my triple, because they all had to be correct. The notation he introduced used an arrow with us writing the first step of execution above the arrow. If R is a program, it can be executed by first executing Q, with P as a continuation for later execution when P has finished. In other words, I can express the I can define the triple by simply saying that Q followed by P satisfies R. It's very similar to the Hoare transition, Hoare triple, just that the operands are in the opposite order. RQP instead of PQR. Now, Robin Milner did not actually give this law for sequential composition because he didn't need it, but it's a very obvious law. It says if R can be executed by doing Q dashed first and then doing S, and S can be executed, this is the second antecedent, the S can be executed by doing Q first and then P, then R can be executed by doing Q dashed first, by doing a composition, a sequential composition of Q dashed then Q, still leaving P as the continuation to be executed afterwards. Now, this law too can be proved very simply from the axiom of associativity of semicolon, but the reverse equation, the reverse implication does not hold. So what we have proved so far, in summary, is that in the case of the law of sequential composition, the algebraic law of association is sufficiently strong to prove the validity of the proof rule for the Milner transitions, and also the proof rules for the Hoare triple. It says the same thing. There was really no need to introduce a new notation just to express these two proof rules. It could all have been done with an algebraic law. Now the final, so this is how the algebraic law is used. It's not used direct. It can be used directly in a program optimizer, which follows the law or even the refinement law by replacing an R by something which is more efficiently executable. And these are validated directly by algebraic laws and algebraic transformations, and they can be computed by simply symbolic execution, again using the laws. The algebraic laws are also used indirectly when the Milner transitions are used to specify or guide the design of a compiler or a generator for the programming language, and the Hoare triples can be, and the same algebraic laws can be used in the design of a program analyzer, such as those which removed the vulnerabilities from software that is still being written today. Now, are the algebraic laws true? Well, my argument here is based on the fact that there exists a simple programming language, the one designed by Kleene, which obeys the algebraic laws, which Kleene called a regular algebra. Well, everybody calls a regular algebra these days. And all I have to do now is to show that the same techniques can be applied to the other operators of a modern programming language, in which there are a great many, like conditionals and loops and so on. This work has been done. Some of it has been done, and some of it remains for future research. But I will just concentrate on how I can use the same strategy to deal with concurrency. Concurrent composition, thank you. I'm going to introduce a new operator for which say that two programs must be executed concurrently. I use parallel bars because this is sometimes called parallelism. And the informal definition of the parallel bars is that the two operands start and finish together, but while they are executing, they may communicate with each other and also interact with their common environment. The algebra doesn't say all of this, but the algebra is all, I believe, true of programs which have communication between concurrent processes, as indeed in communicating concurrent systems of Milner. And I'm going to treat this parallel combinator as entirely on the same basis as the sequential combinator. It's just two ways of executing a program, either concurrently or sequentially. And therefore I'm going to I'm going to formulate the algebraic laws for concurrent execution in the same way as that I have done for sequential execution. Unfortunately, they are the same laws. The concurrency operator is associative, it's commutative as well, and it's idempotent. And it distributes through union, and it has as its unit the same unit as sequential composition, which is do nothing. If you do nothing in parallel with something, it's the same as doing something. Doing nothing, in fact, does nothing. Now, there is a new law, which I discovered only recently, well, 5 years ago perhaps now, called the exchange law, which plays a very important role in the theory of programming. The exchange law is written as an axiom on the top of this slide. Its purpose is to validate a possible method of implementing concurrency by interleaving of the atomic actions of the two concurrent threads. You can see that in a certain sense, the left-hand side of this law is more interleaved than the right-hand side. The right-hand side is more concurrent than the left-hand side. Well, when a concurrent program is run, the actual choice of which interleaving is executed is very often made by a scheduler at runtime. So I regard the exchange law as expressing one of the decisions that a scheduler is allowed to make when it is executed, or a compiler for that matter. I don't mind whether the choices are made at compile time or at runtime. the right-hand side calls for concurrent execution of two threads, each of which is a sequential composition. And so on the right-hand side, I have two sequential compositions marked in red. Supposing the scheduler makes a decision like this, I will run this parallel program, making sure that the two semicolons which I have marked in red will be passed by both the threads simultaneously, as though they were synchronized at this point. And that is my choice. As a result of that choice, the actual execution which results is shown on the left-hand side. It is a sequential composition of two parallel compositions. The sequential composition on the left-hand side represents the simultaneous reaching of the two semicolons on the right-hand side. And therefore, everything that happens before the semicolon on the left-hand side is the same as what happens before the two semicolons on the right-hand side, and those two things are done in parallel. And similarly, that's the P and the Q are executed before a red semicolon on the right-hand side and on the left-hand side. And similarly, the P dashed and the Q dashed occur after the red semicolons on the right-hand side and after the single red semicolon on the left-hand side. That is an informal justification for this law. From the exchange law is the most complicated law that I really want to show you today, because it has four operands, three operators on each side of an inequation. You very often want to use the frame law in a context in which you've only got three operands or even only two. That's okay. We have a number of corollaries of this law, which I call frame laws, which I've written down 1, 2, 3 on this slide. They are very, very simply proved. Consider, for example, number one. Number one is the same as the exchange law, except that it doesn't contain one of its operands, P dashed. So from the axiom, we are permitted to replace P dash by a special case, namely the do nothing instruction. If when we've replaced P dashed by do nothing, we can cancel all the do nothings. And this will give you the law number one on this side of the theorems. The third of these theorems describes the two ways in which the actions of the two threads can be two threads consisting of two atomic actions can be interleaved. One of them goes first, or the other one goes first. They are both in equations, which means that it is also possible a third alternative. For example, two atomic actions may be executed simultaneously, absolutely at the same time. And that is not excluded by the exchange law or either of these axioms. And it's this that means that my model of concurrency can be given the title true concurrency, as opposed to the concurrency which is defined by sequential composition. The sequential consistency principle, which says that concurrent execution is equivalent, i.e. equals, the union of all the interleavings of atomic actions. There are many, it seems very beneficial to allow true concurrency as well as false concurrency in my model. Here's an example of how to use the exchange law to actually compute an interleaving. I'm going to write two strings, a red string, ABCD, a black string, XYZW, and I'm going to assume that I've just omitted the semicolons. I'll put them back shortly. These two programs are executed concurrently, and I would like to see how to derive at least one of the interleavings. Well, the first thing I have to do is to act like the scheduler. I have to choose at what point do I wish these two threads to synchronize, and I will write semicolons in those two places. That's on the second line of the slide. And then I can apply the exchange law. This matches exactly the right-hand side of the exchange law. So I can move the components x, y, and a to be done in parallel, and b, c, d to be done in parallel with z double, z, w. And that's done on the third line, by application of the exchange law. Now, I'm going to make another decision about which of the semicolons to choose to do the scheduling. In fact, I can now make two decisions, one applying to the left-hand side of the main semicolon and one to the right-hand side. And that's done on line 4. On line 5, I've applied the frame law to the three operands before the semicolon. And on the last line, I've omitted a lot of steps. I've chosen to perform x before a, and so that the resulting string begins with xa. You can see that this is an interleaving. We can get many other interleavings of the same string by making different choices at each step. Where are we going to put the semicolons? That's an arbitrary choice. Should we apply the law of commutativity of concurrency before making this step or not? These choices will affect which interleaving I get as the result. Of course, there's no commutativity law for semicolon. And that is why the original ordering of the two threads, A, B, C, D, and X, Y, Z, W, is preserved. There's no law that enables us to exchange any of those, as you can see quite easily from the fact that I've put one of them in red type and the other one in black. Proof rules for concurrent composition. Well, let's see. Just as I want in the next 3 slides to derive a proof rule for concurrent composition similar to those needed for sequential composition. The proof rule is modular, just like the rule for sequential composition, in that it splits the proof of a complex formula written after the line, the consequent, into 2 simpler proofs which are written before the line. In the case of the law that I have on this slide, the antecedents of the proof rule are simpler because they only contain 3 operands instead of 6. And they're simpler also because they contain sequential composition rather than parallel composition. So it's win-win. It's a very good way of splitting proofs of concurrent programs. You prove the individual threads separately. And this rule is proved from the exchange law, but this time we can actually prove the exchange law from the rule. Here I'm going to give you a proof that the modularity rule implies the exchange law. It really is very much an undergraduate exercise. I've written the modularity rule first because that's what I'm allowed to assume in proving the exchange law. And my first step of the proof is to replace the R and the R dashed by P semicolon Q and P dash semicolon Q dashed. The antecedents are now, as a result of this substitution, just statements of the axiom, the basic theorem of reflexivity of refinement ordering. So we have already proved those. We can therefore deduce the conclusion of the rule, but the conclusion of the rule after the substitution of R and R dashed makes the conclusion equal to the modularity rule. Therefore, equal to the exchange law. So here's a little proof which uses the exchange law as a proof rule, and it concludes with the exchange law. Sorry, I'm getting confused with the next slide. It's a little proof that uses the modularity rule to prove the exchange law. The exchange law implies the modularity rule. You can see the proof is no longer than the one I've already given you, and therefore, since as usual time is pressing, I will omit it. But just summarize, if we take the modularity rule, which is shown as the third rule on this slide, and we translate it using the definition of the Milner transition, in one case, on the second line, and the Hoare triple on the other, just translating the PQRs into RQP or PQR, and into Milner notation or to Hoare notation, they are all the same. The modularity rule I have shown is equivalent to the exchange axiom, and therefore both the rules and by definition, by the very definition, both the Hoare triple rules and the Milner transition rules, the verification semantics of your program and the execution semantics are the same. So, summarizing, in the case of the exchange law, we have proved it equivalent to the Milner transition, which he used in his definition of CCS to explain concurrent composition of two communicating concurrent processes. And we use it again to prove the correctness of the Hoare triple, which is for proving the correctness of programs. Again, the regular languages are a support for believing that the law is true. They are at least, as the logicians say, a model for the axiom. So, in praise of algebra, I think algebra is wonderful. Algebraic laws are so simple they can be taught to school children. Their elegance is much appreciated by mathematicians and by theoretical computer scientists. Algebraic laws are actually used by engineers for symbolic computations. Mathematicians tend to rather despise symbolic calculations. If they have a proof that they can do by symbolic calculation, they never tell you how. They just say, by calculation. And I don't follow this example, I'm glad to say. They are used indirectly by software tools. The software tools use the Milner transitions to define compilers and interpreters, and they use the Hoare triples to define verification principles. But nevertheless, since both of those are defined by the algebra, they are indirectly using the laws. And as we saw, they play a central role in the unification of the theories of Milner and Hoare. And so, anybody against? Let me ask you.
Questions? Thank you very much, Tony.
Thank you.